Hi friends, in today's lesson we'll be solving systems of equations using the algebraic method of substitution. In this lesson we'll only be looking at systems of equations where the equations in the system are both written in slope-intercept form. And you'll see for each of these examples I also provided the visual graph of the system of equations just so that we have a reference to match our solution to. But typically when you're answering a question like this, you don't have the graph in front of you. So what we're going to do is we're going to start by substituting the y value in the original first line with the expression that represents y in the second equation in the system. So really what that looks like is just setting both expressions that are equal to y equal to each other. Now that we're here, we need to move the variable terms to one side of our equation while keeping the constant terms on the other side of the equation. So since my largest variable term is on the left, I'm going to move my other variable terms to the left side of the equation as well. I'm going to add 4x on both sides. That'll cancel out the variable term on the right. And I'm also going to subtract 1 on both sides of my equation, which will cancel the constant term that's on the left. So now we have 3x plus 4x equals 8 minus 1. Then I can combine my like terms. So 3x plus 4x is 7x. 8 minus 1 is 7. And I can isolate my variable by dividing both sides of this equation by 7 so that we get our x value, which is equal to 1. And I can see that on my graph. The x value for the solution to this system is x equals 1. Now that we found one of our variables, we have to go back and find the other. So since we found x first, we're going to use one of our lines. I'm going to use the line y equals 3x plus 1. So taking one of the lines from our system, we're going to plug in or substitute in the solution we got for our variable x. So I'm going to replace x with 1 since we solved and found that x equals 1. And now I'm going to simplify this so that I have my value for y. First, I'm going to do that multiplication. 3 times 1 is 3. And now I'm going to add 1 to it. So I get my y value for the solution to this system, which is 4. And I can visually see that on my graph here as well. The y value for our solution is 4. So once we're done algebraically solving a system of equations, then we can state our solution as a coordinate or our point of intersection. So my solution to this system is 1, 4. For my second example here, I have the equation y equals 1/3 x plus 3 and y equals 2x minus 2. So again, first I'm going to substitute y equals, which is basically going to look like me setting both expressions that are equal to y equal to each other. Now, the coefficient for x in one of these expressions is a fraction, but nonetheless, we'll just do that fraction operation in our calculator. Don't stress yourself out trying to do that fraction operation in your head. We're still going to start by moving our variable terms to the same side and our constant terms to the same side. So I'm going to subtract 1/3 x on both sides. Just because personal preference, I like to move the smaller variable term to the same side as the larger variable term. And then I'm also going to add 2 on both sides, so that way I've canceled out my variable term on the left and I've canceled out my constant term on the right. So on the left side of my equation, I have 3 plus 2, and that equals the right side of my equation, which is 2x minus 1/3 x. Now I can combine these terms. So 3 plus 2 is 5, and 2x minus 1/3 x is 5/3 x. And now to cancel out that fraction coefficient, we're going to multiply both sides of the equation by the reciprocal, or by the flipped version of the fraction. So when I multiply both sides of my equation, by 3/5, because that's the reciprocal. It'll cancel out the fraction on the right side, leaving me with 3 equals x when I multiply 3/5 times 5. So now I know my x value for the solution to the system. And we can see that on the graph as well. The x value for our solution is 3. If we successfully calculate this y value for the solution to our system, we should get 4. Now, because line 1 has a fraction coefficient for x, and I don't like to play around with fractions if I don't absolutely have to, I'm going to use line 2 here, which is y equals 2x minus 2, in order to calculate my y value for the system solution. So I'm going to substitute x with 3, since we solved the system already for one variable. Now I'm going to do that multiplication. 2 times 3 is 6. And when I subtract 2, now I have the y value for my system's solution, which is 4. And I can state my solution, or my point of intersection, as 3, 4. In this example, we have the equations y equals 2x plus 13 and y equals negative x minus 2 for our system of equations. On the graph, I can already see my solution is going to be negative 5 for the x value and positive 3 for the y value. So I'm going to proceed by setting both of these expressions that are equal to y equal to each other. The left side of my equation has the larger variable term, so I'm going to add x on both sides, and that'll move my variable terms to the left side of the equation. And I'm going to subtract 13 on both sides of the equation to move my constant term to the right. So on the left, we have 2x plus x, and that equals the right side of our equation, which is negative 2 minus 13. When I combine those like terms, I have 3x equals negative 15. And to isolate x so that we have the x value for the solution to the system, I'm going to divide both sides of the equation by 3. So I have x equals negative 5. And that's exactly what I expected, since I had this graph here that I could visually check as well. And to calculate the y value for the system, take either one of your lines. I'm going to take the first one, y equals 2x plus 13. I'm going to substitute my x value into that equation. And now I'm going to simplify this so that I have a value for y in this solution to the system. So when I do that multiplication, we have y equals negative 10 plus 13. And when we add 13 to negative 10, we get the y value equals 3. So our solution, or our point of intersection, is negative 5, 3 for this system of equations. For this last example, you can already tell by the graph that this system has no solutions. Visually on a graph, if we see the graph of two parallel lines, there is no solution to the system. Or if we recognize in the equation that both equations have the same slope but different y-intercepts, there is also no solution. But let's say we don't recognize those immediately and we go to solve this using substitution algebraically. We would set those two expressions equal to y equal to each other. So I have negative 3x minus 2 equals negative 3x plus 5. And when I move my variable terms to the same side, or if I add 3x on both sides, they cancel out on both sides of the equation, leaving negative 2 equals 5. But unfortunately, that's an untrue statement. Negative 2 will never equal 5. And the reason this happened is because both of our equations have the same slope. These equations will never intersect. They will never overlap. There is no solution. So I can't calculate the other coordinate, and my solution to this system is no solution at all.